I'm very lucky to have Anand Sivaramakrishnan talking to us today about an overview for the NIRISS Aperture masking interferometry mode.
Okay. The mic okay? Right. An overview of the NIRISS Aperture masking interferometric mode. Is a Canadian instrument, and it's built on the op bench on the other side of the fine guidance sensor JWST. And the aperture masking interferometric mode is demonstrated right here in this first slide, where I have a full aperture point spread functional image of a star. Here's more or less. Forget dots. That creates a typical point spread function you expect from a telescope. And masking interferometric mode is implemented by basically the entire aperture and letting through only the light through the holes, which is done with a mask in the pupil wheel of NIRISS, in the pupil plane. That creates an image here shown the same stretch. Why you want to mess up such a beautiful point spread function and make it look so ugly. There's reasons for that. One is that the very core of that PSF is considered brighter than the surrounding pixels. As the core of this image at the same wavelength is brighter by over times in some sense. And the other is that the structure around here is highly repeatable and enables one to calibrate out the telescope. And that's basically what aperture masking interferometry does. That is the sky. There's two instruments in one box. One is the fine guidance sensor, which is really for NIRISS because that makes NIRISS astrometry very reliable. Since it's bolted to the fine guidance sensor, which does the steering. Not the FGS. The NIRISS itself operates in near infrared on very NIRCam long wave. 4 observing modes, and its science drivers are high redshift galaxies, first flight, like JWST's original intention. Spectroscopy for transits and eclipses, and then the E mode brings moderate contrast but high angular resolution imaging, which you can use whatever you want. Exoplanets, transition disks, active galactic nuclei, volcano, exosolar studies in nearby stars, and wavefront sensing and control. Well, not part, but wavefront sensing. The ASC is primarily with 3 medium band filters and sometimes with a wide band 2.7 micron filter. I'll outline the science motivation or a few science cases that make AMI interesting and the basic principles of how AMI works. It's specialized science because it's moderate contrast, unlike a coronagraph, which is high contrast. Because the coronagraph actually throws away starlight, whereas we get all the light and look near the star, for example. So we still have photon noise. And it's a high resolution science, even if it's not necessarily high contrast. Also using wavefront sensing. I'll go some of the operational details, give you an overview of how to use AMI. And look at data analysis, which is probably the most opaque thing in aperture masking from JWST. Everything else conceptually very simple, but this steps into an interferometric mode. And then show you science programs, a few GTO and a few programs that are still up for grabs. To show you how you could make interesting science programs using AMI. does is it goes very close, 40 milliarc seconds up to, and it's useful about 400 or 500 milliarc seconds from a bright star, or separation between things you want to see. And it goes up to almost 10 magnitudes of contrast, which is 10 to the 4. It goes, we'll be able to do 9 magnitudes from simulations so far. I'll show you the filter set, about 4 microns with attention. And here's an example of a simulation which either David Lafreniere or Etienne Artigot did. And this simulation is a 1 exposure of various stars at 30 parsecs and 820 megayears. So you ask yourself, what can you see around these stars if you look at them like this? And at this separation, you reach these contrasts with the AMI mode. That's 0.1 arc seconds or 100 milliarc seconds. And the color is pretty flat outside that.
The JWST, I didn't compare the other JWST.
Oh.
How do those compare with the other JWST chronographic?
The JWST chronographic modes kick in at 400 or 500 milliarc seconds at the similar wavelength band. They're out here on the right, which is what makes AMI interesting. As you can see, it's niche science because out there we drop our contrast even further down. And that's to get rid of light. We have to deal with the light.
Are they reaching magnitude 12?
Yes, right, the limit. That's important. So we observe a brighter and brighter. We actually reach a limit of contrast we can do with AMI that we expect we can do, and 9 magnitudes. And at one, we don't quite reach that with the late M and L dwarf. So the science you can do with this kind of contrast is detecting or characterizing planets near stars, nearby stars, feeding structures in active galactic nuclei, transition structures and planets that create structures, star binarity. Now that's brown dwarf binarity, or even dwarf binarity, where the are quite low, and even though the objects are faint, you can still do a reasonable amount of time with AMI, but you cannot do them on the ground with adaptive optics because they do not feed the AO system with enough light to perform AO correction. So I think that is our specialty. We are pushing detection of extras of zodiacal light around extras, of which there are many. So we look at nearby stars and see if we can see the zodiac from them. And then we can also do the high resolution solar objects like which is nearest of the closest is Galilean moons, and it's ripped apart by also it's got a terrific summer cake from Jupiter being close by and tidal forces, and it's very volcanic. It's very active. The AMI mode, the niche mode, it complements NIRCam. This is the NIRCam spot, and we work behind the spot. Here, sort of one Jupiter mass planet at 1 AU around 0 dwarf at 10 parsecs for observation. So this is kind of grist mill. Why is AMI relevant at all? Kindergarten level. So here's the spread function from a full aperture telescope, and it has a core, which has a radius of 1.22 lambda over d. The fringes, if you create two holes in an aperture mask on that telescope, right at the edges of the telescope, are spaced by lambda over 2D, half lambda over d, compared to 1.22. So it's 4 times, 2 to 4 times better in resolution. And the nodes, of course, have a big dot around it. The key is throw away light with lower angular resolution. All the shorter spacings on the telescope contain only the longer spacings, and so we get better signals at the highest resolution that the aperture offers. There's nothing cool about it. Is on a near-infrared imager of the spectrograph, and this is the design of the instrument with a pick-off. Here's the telescope focal plane, out of mirror sends the light to a anestigmatic collimator. It creates really good pupil image. It's the best pupil image quality of all of JWST, and the only reason I might change my mind is Randy says I'm wrong. But it is really a spectacular pupil image compared to all the other instruments. One reason is achromatic. And this non-redundant mask sits in the wheel there of a wheel which contains filter and pupil. And this light is then focused to a camera with 60 milliarcsecond pixels. So with the mask itself, you have 7 holes. 7 times divided by 2 is 21 baselines. And vector baselines repeated, which makes the images highly calibratable. You can use scope effects, see the sky structure better. The hole is to pupil shear. We don't know exactly where the pupils are going to fall on this plane. And that the whole mask 15% throughput, and the peak pixel is a 40th of the full pupil. So much better for brighter objects, because we're throwing away a fair amount of light. It has, other than science, it's used for target acquisition for the single object slitless spectrograph, which is a very high dispersed, defocused planet transit spectrograph. And enables wavefront sensing. Yeah.
Is there a particular advantage to keeping the holes hexagonal as opposed to just making them round?
We haven't.
Could you repeat the question?
Yes. Is there a reason why the holes are hexagonal? Either would have higher throughput, let more light through, which is true, but they're a headache for data reduction. So that's a very wise question. Here's the pupil wheel, the filter wheel. The NR mask is here, and it's used with those 3 filters and a 4th one. Sometimes use the clear filter on fainter objects, much fainter objects, and do a new type of data analysis, which is similar to AMI data analysis, called kernel phase. The reason this wideband filter is interesting because even though it's these are not Nyquist samples, is that it has water band in it, and that enables break accuracy and determine log G and the effective temperature of alien and Jovian planets, Jungian planets. So basically said that, and these filters give you about 9 magnitudes, and you get maybe so less to get these numbers with the F277, but it's still useful. There's a rare which has a lot of detail on that from the scientific point of view. Now, this famous eye chart from the JWST is how we read out the detector. Luckily, if you're observing an AMI, you don't have to worry about many of the details on this. read the detector, there's a bar over there, and they're grouped into a group. So these are, and we only have one frame in a group, so this whole thing is simplified for us. A user would know is that an exposure comes out in a single FITS file. So that scheme is simplified. It's a subset of the previous one. We have frames. One frame is one group. There's no averaging. We just get that frame, that frame, that frame, and it goes up until we hit some kind of saturation that we don't want to go above in the pixel and the brightest pixel, and then we reset and keep going. So that's an integration. And this has an keeps on, but this is NIRISS rapid, one frame per group. And we use an 80 by 80 pixel array. It's all possible to use the full frame, which takes 10 seconds to read out. Whereas 80 by 80 frame takes about 15 seconds to read out. So here we have an AMI exposure with 5 groups. 1, 2, 3, 4, 5. Then you read 4 integrations. So the duration is number of groups times number of iterations times the frame time. This is difficult for people not JWST because the nomenclature is a little different from what has been used over the decades in infrared detector handling. So this is a helpful plot. Now it's throwing out light with small holes and a big PSF on the detector. Our brightness limits are pretty amazing. We observe a 2.6 magnitude star or a 1.6 magnitude star with AMI as an imaging instrument. We use 2 groups or more groups. This is a better graded mode if you don't use just group. And estimates, they go around 3 for the medium band. Not as well calibrated is that we don't save the detector that is performed at reset. So we use kind of an average for that. And saturation is 72,000 electrons with a percentage PSF. So that's generally what we use for our exposure time estimates. We don't want to saturate. If you use clear or clear P filter, the P is because there's a little object in the middle of that which is a pure alignment. It's called a PAR. So it's a clear with PAR, and that's a clear P. So that's like a full pupil. Then you have 4 magnitudes fainter than each of these. And if you want the 10·7 second full detector read, then you have another 5.5 magnitudes to those. So that is the faint and far away object regime, more very cool brown dwarfs, things like that. We're going to go for brighter objects because we know more about them from the ground and use sub-80, the AMI subarray. How do we plan to operate AMI? We target acquisition in 64x64 array, which means that array is read faster than the full array, than the sub-80, which means we don't expect any saturation. It's an odd number of groups, up to 19, and we should try to avoid saturation to enable detection where the center image is. And it's read out with a rapid readout. We are in the 480M mask. Bright objects, and in the P mask for fainter objects. We know where the star is. The telescope performs a small angle maneuver to place target where you're looking at in the first position in the sub-80 array. So you go to pos 1 after your target acquisition. The wrinkle in that, I'll get to that later. So once we're in the 80 by 80 array, on the side of the detectors, we lose 4 rows to insensitive reference pixels. That with NIRISS Rapid, selecting n groups and n specifies how to do it for an exposure. If you need more photons, you just have more exposures. Use 1, or you can go to pause 1, then pause 2, observing the same way each time, or 1, 3, or 1, 2, 3, 4. You can't go 1 and then 4.
All those pauses are on the left side of the detector. They're on the right, so they all have reference pixels.
They all the ones are in AMI sub 80, in sub 80, and this has the reference pixels down one edge. Depends which way you look at it. Science frame, they seem to be in DS9 at the bottom. Detector. Yeah. Moving the target from your target acquisition to pause 1 is expected to have about 5 milliseconds placement accuracy, which is a requirement. So we're hoping that happens. And you offset from the position you want. I don't think you have to specify the same offsets for each position. I'm not sure about that. I said 15th of a second frame time. So if you've got hands, you can hand hold JWST and click. The full design is possible with optional target acquisition. You don't have to use it. And it's also in this rapid mode. So the detector, the bit of it using is 80. Reference pixels. This is not a science frame. This is in what we call our detector frame. The science to flip that over and then downward from the bottom left. Here's the reference pixels. This is the flat field, and it's a very stretch. We were looking at the quiet area of the detector. We could very sensitive to flat field error. And so one area, pause 1, which has a really quiet flat over there. We looked at pixel to pixel as well as longer scalations and use that. All the have our drivers. We do positions 2, 3, and 4 up to not have the NRM PSF sort of the PSF fall to where it used to be because of persistence. We don't want persistence to affect after images to affect the data. So we move far enough away. Got with some bad pixels here and there, but we found 4 positions. Is in this area, which is on roughly the same scale as here. For FT, the image is a little bigger, so that's why these bigger circles indicate where you expect most light to fall. So you actually plan your observation. Science targets you want to look at, and you want some kind of calibrated star, a cal star, to give you a set. Use similar spectral types and brightnesses. Mainly, you want to avoid strong lines in your calibrator that don't exist in your science target. Not as sensitive as curve subtraction, but it is somewhat sensitive in the more demanding cases. Require is a non-interruptibility between observing the cal star and the science target. So we don't need primary to be edited or the secondary, especially if you are above about 4 or 5 magnitudes. You really want to be careful. That makes scheduling a little bit harder. we always same positioning because we want to get rid of the effect of flat field errors. And shooting for the middle of the pixel, if you don't set, might change mind later as we understand more of the algorithms. The high contrast observations to have less between the two, which is why it's non-interruptible, rather than have them close in the sky. Where JWST doesn't move as much, and we're looking at that as well. It doesn't seem to have a terrible effect on the PSF. The drift, basically. So take a calibrator in quick succession, actually non-interruptible. In the we want it non-interruptible, which means no engineering activity in between, whatever that is.
Hours or minutes?
Well, it'll be hours because of time. 30 minutes if it's one after other, but it has to be. If it's not, I'm not sure if it's going. It's sequential. Is that right? So
it will be sequential. It can be. If we say sequential, then it will be sequential.
So repeat it.
If we say it is sequential, then it will do sequential. But if we just say group, it will do it.
We could have other observations. Okay. The question was how could we have to go to the Cal star? And if we specify non-interruptible, other observations can occur in between first observation and our second observation. Sequence restricted condition where we have to go right away to the Cal star or our next target. So if wavefront sensing control doesn't occur but once in 2 weeks, it could be 10 days.
You leave the mask in place, so you worry about repeatability of the mask.
We don't leave the mask in place.
Back accurately.
You ask all the hard questions. But they're all okay. Since how to select calibrated stars, they ought to work to be selected. They shouldn't have funny spectral lines, shouldn't be binaries or triples or have infrared excesses. So you can catalogs with web. You can actually do masking from the ground with KEC or Mesosphere or LBT, or go to interferometers like LBTI or VLTI and look at your calibrators. But that needs some preparation. And again, applications, high contrast, we do want triple observations. If you're not looking for very high contrast, you're looking for brown binaries. The contrast might be 1 or 2 magnitudes. You don't need to worry about taking a calibrated star. We expect it will be plenty stable to use a large calibrator or use a synthetic PSF, a software PSF. And where possible, amongst the GEO community for AMI, to share calibrators between programs, and that saves a lot of time. More work and more planning, but it's a very useful thing to do. So I made the exposure time. There's a rule of thumb which is very easy to remember, and it's published in literature. If you're looking at binary with cells, you need a contrast ratio squared photon. So if you want a ratio of that's 10 to the 6 times 108, you need 10 to the 8 photons. That's a rule which has some simulations and data on the ground and seems to hold with our simulations in JWST. The way to do binaries is to actually simulate the position with the exact mask placement you expect, and do a full Monte Carlo Markov chain Carlo binary search and figure out what your contrast, what your exposure times need to be that way. We do have official ETC, and there are several unofficial ETCs. There's one available publicly, which are not guaranteed to be at all, but what we've had to use before the space ETC came online. So that's fairly easy. The complicated scene, it gets much harder. And you really rely on your own relations, and this has the team ET, which is not official, has a simulation code which you can simulate binaries or input scenes with. And then reduce fake data and see what you can get and determine your exposure times from that. So that is a noise model you put in. Or in Python, so you can edit, change the noise model if you want. Noise parameters. So this you have to do your own simulations, and complex extended objects, you also have to do the same. There are these methods from interferometry, especially the optical interferometry, where some likelihoods with regularization is a little bit of a art, but after you start looking at it, you realize that there is some sense in these crazy choices of how you rise your imaging. The package from Laurent Mounier in France, which is used a fair amount. Fabien has a squeeze package. He's from Atlanta, from Georgia. And Jean has Jean Monier's MACIM. So these are available and are used from the metric community quite a lot. You need how much information is used, how visibility is used. Radioscopes typically don't use phase information as much as closure phase. Our phases much more directly. The radio don't have very good flux information because they're asked to put a huge DC signal on everything the telescope looks at. So all they get is phase information, mostly. That change, but that's how it is now. Information, I'll get to that in a second. Once you get there, it's through standard calibration pipeline, linearity, flat field, cosmic rays, that sort of stuff. And you get calibrated image out. And then plan to do one or two things depending on JWST stability and whether you want to look at bits of the data separately and assemble statistics or do everything all at once. When all at once, we just average all the exposures in one file image, combine them how, or we can a given exposure, and then we have n images, which is understanding your data noise properties. Then you observe from the data to get the science, or to work on to get the science. There's bases, as I pointed out. One is fringe amplitude and fringe phase, or Fourier phase. Fringe is called visibility, and the total flux. And very simple for very simple models like binaries or 3 stars, maybe 4 stars. That's in case B is use the entire image for reconstruction. In this case, the calibrated PSF and the target PSF after the calibration goes to analysis software. So look at this. Here's an image, simulated of a point source. 30 m, the 4 point and the square root stretch. So you can see there's a lot of structure, a lot of light here, which contains plenty of information. brightest pixel doesn't contain that much information, surprisingly. So there's 7680, which is almost 6.4K independent pixels of information. So we mask, and we take data through the mask, Fourier transform this data, we get this complex array. I've only shown part, or actually the absolute value, but it's a complex number array. And it has a splodge, which is basically how bright the star is, and other splodges here. Each splodge is a certain distance from the center of the image, and it corresponds to a baseline. And as I was pointing out, how about mask rotation? We probably need to determine the exact rotation of the mask from the data each time. 42 splodges, there were 2 baselines. Splodge is actually repeated in some weird way there, so that this splodge is not independent of this. They're almost the same splodge. They're complex conjugates of each other, if you want. So you have these 40 bits of information, or you can condense this into 42 bits of information, plus a box and a pedestal on the image. So that makes you 42 numbers of morphological interest and 1 number of photometric interest. Those are the visibilities and fringe phases, or Fourier phases of each splodge.
Yeah. So what we're looking at there on the right is the real Fourier transform, or
No, it's the absolute value of the Fourier transform.
That's the amplitude. Square.
Give me the square of the absolute value because it shows better. There's information in those holes. That's something that image reconstruction has to deal with. You can't tell Fourier components of your image if you haven't measured them. This is basically Fourier space inside in some sense. So what do these 42 plus 2 bits of information, pieces of information? Well, how do you get them? You could numerically transform the data to a complex number array. It's somewhat easier to understand, but it's not all. You could do it without any trouble. We know the splodge heights, which are the visibilities, and the splodge phases, complex number, get our observables. The problem is bad pixels in the image really mess up a Fourier transform because of ringing, and because our detector is not hugely coupled, it's not very fine sampling, we can't identify bad pixels as being very different from their neighbors. Can't dither either because of the problems. So we had to get rid of the bad pixels somehow, which is tricky. Conceptually, that's what we do. In real life, well, on simulated data, we have an analytical model to the image. It's surprising that this data has an analytical model, but it actually does. And when that model, you get out your 42 quantities, actually 4, including the flux and the pedestal, from a least squares fit. It's just one shot. You do determine the pupil rotation from the image. Assuming a huge number of bad pixels, you can do. And once you're in phases, you can calculate things called the closure phases and square the visibilities, which is typically what feed into binary or triple models to fit among the data. Implemented in our pipeline. with the fringe, we can calibrate out the instrument by measure the closure phase. The baseline corresponding to each of these spacings have a fringe associated with them. And if you have 3 fringe phases, you get 0 if the source is a point source and your optical system is not aberrated. Even if your optical system has phase aberration, you still 0 closure phase, because the phases cancel out in going around the triangle in a cycle, in a cyclic way. So phase aberrations cancel out if you measure these phase differences from this image. 3 splodges, add them up. These cancel. You're just left with other source error and astrophysical signal, which is here. So from a faint companion is in there. As I said, for point source, the closure should be 0. So what we in this slide is that you measure the calibrated closure phases, subtract them from target closure phase, and that's rated closure phase. Just don't measure any structure that is symmetrical middle, about the center. But the fringe visibilities do. And so measure the target visibilities by, and calibrate by dividing by the calibrated SF visibilities. This is a point, that's a point source, we get 1. And we, those are the 2 quantities that go into a lot of the interferometric data analysis. There's packages out there. After the initial image calibration, which we're not developing here, the expertise are out in the community. The other STScI image and sometimes a re-estimated point spread function. It depends on some details how you handle the regularization in the image reconstruction. If you use least square difference, but convert to a finer, you get sharp structure. If you use an absolute difference as a measure of your error, you get more extended structure, and there's other ways of doing regularization. Even paint area with different regularizers, like one for a source area, like an AGN, different one for around the AGN. So there's lots you can do, and still be enough to publish. There's been work in the literature, and there's work in the literature on these methods. So for science, in the diagram, we're going to observe calcium 15, most likely, to distinguish between this structure, plant structure, ambiguous detection of planets, and a lot of confusion that has resulted from ground-based data. So we're going to detect, confirm, disambiguate, or follow up suspected protoplanets in this transition disk. Do is look at Eta Corvi, which has a dust disk, and if you look at Corvi and look at the fringe visibilities as a function of baseline length, normally you expect something like this, which is, this is 9.6. It's almost 1. It's a very good fringe. So there's a very disk around it that is slightly dimming the contrast in the fringe. And if you look at the disk by 100, you still get a detectable signal, we believe. This is where STScI comes into its own from the point of view of photometric stability or fringe visibility stability. On the is around 5% on visibility, so you can see that we expect to do a lot better. I put this in because it's actually quite important. Omni mode and its methods of analysis provide a wavefront sensing backup method for NIRCam, where you phase the telescope by tilting during commissioning, for example, into pointing. The red ones point one place, the black a different place, and so on. You can coarse phase them using mirror analysis, secondary mirror and primary mirror commands. And you can also combine ends with a full pupil point function and follow the telescope over the whole pupil using indications of the Gershberg-Saxton method, which Alex Greenbaum and I published, so I call it GS method. This is the backup for fine phasing. We don't go out of focus, we don't move any segments. So, that helps sleep at night. The high resolution of NRM is, of the E mode, is useful for science on Io's volcanoes, where the volcano photometry needs to accurately observations in order to study its inner. And if you can AMI image with Io, of Io, and put it through a Laplace filter, look for fine structure, or a Laplace-like filter, deeply simulated the disco with the volcano and without volcano, a still volcano, not a really bright one. It's just that it just jumps out at you. So resolution is also very useful because there will be volcanoes around or surface regions in brightness. We plan to observe Io with F430M in AMI, and this ability of photometry from space or through the telescope is of a ground-based adaptive optics. So in NIRISS brings moderate contrast but smaller working angle and high resolution imaging, complementing and it also a great end filter. It enables imaging of things as bright as 2 and 3 magnitudes. And it offers backup wavefront sensing as a comforting background cam. And here's links and the complete tutorial on setting up the astronomer proposal tool for an proposal, which we'll include inside the slides from this talk. And that is the talk. Thank you.
Thank you very much, Anand. Does anybody in the room here have any questions? Please wait for the microphone so that people online can hear your question.
Hi, is 7 the maximum number of apertures you can have and still have the non-redundancy? Because you've had 8 apertures and better contrast then?
It comes with the second mirror struts cutting through apertures, so Peter's expert at making bits of metal in them in a non-resonant pattern, and it's quite a search. 7's the best, and we picked the ones with the biggest baselines because we wanted resolution.
Question? No? Are there any questions online? If you're on WebEx and have a question, please go ahead and unmute yourself and ask your question.
Hi, it's Jonathan, also on the NIRISS team. I was curious how comparatively between NIRCam wavefront sensing accuracy and the NIRISS ME, would you be able to calibrate say over a 2-week period if you have an AME observation early in the wavefront sensing and then late in the wavefront sensing on NIRCam schedule? Could you calibrate back to show like how comparable the data is over say a 2-week baseline?
I think we meant wavefront to equivalent of a pretty high Strel ratio, 75%, maybe somewhere between 5 and 100%, not 100% Strel. So we're in spitting distance of the of being able to test NIRCam's wavefront. There's also the problem of non-one path error between NIRCam and NIRISS. I would see if that keeps changing or not, which would be an indicator of something funny happening. So it is possible. I'll have a look at the paper, or you could, the Greenbaum and Sivaramakrishnan, where we have quantitative results in there. It's definitely possible.
Are there questions for Anand, either in the room here or online? Let's go ahead and thank Anand for a nice talk. And we're going to have our next JWST community lecture in 2 weeks, and it'll cover wide field slitless spectroscopy.